Hi, my name is Reinhold Wilcox, and I'm a PhD student at Monash University, which means that I am training to become a doctor, but not yet a doctor in astrophysics. I study binary stellar evolution, which means the theory of two stars evolving together before they end their lives as neutron stars or black holes. This is interesting because when you have a binary system of two neutron stars or two black holes or a neutron star and a black hole, you might one day get a merger and produce gravitational waves, which is a really exciting new area of science. So I study the precursors to gravitational waves.
Hi, I'm Avi. I'm a PhD student at Monash University, and I work with LIGO to find really big black holes. These are known as intermediate mass black holes, and I'm my second year of my PhD, and I'm searching for them.
Hi, everyone. I'm Vaishali. I'm a postdoctoral fellow down at the Australian National University, and I work on developing technology for gravitational wave detectors to make them more and more sensitive so we can observe more binary black hole mergers or binary neutron star mergers or exotic things that we haven't even thought of.
Hi, I'm Adam Batten. I'm a PhD student at Swinburne University of Technology, and I study the extremely low density gas that exists outside of galaxies. And so this region of space is something we call the Intergalactic Medium. It's really, really hot and it's really, really low density. I'm trying to use simulations to understand it more. So I'm trying to work out how the matter is distributed in the intergalactic medium and how did it get enriched with elements like carbon and oxygen and that stuff like that.
Hi there, I'm Johannes Ischoitz, and I'm a postdoctoral researcher at the Australian National University in Canberra. In my research, I'm looking at how we can make the laser mirrors for our gravitational wave interferometers, which are already among the best in the world, even better. And one of our biggest problems is that the molecules that make up the coatings on the mirrors are never really at rest, due to their thermal energy. And to the detector, this buzzing in the coating looks as if the mirror as a whole is moving, which tends to drown the weaker gravitational wave signals in what we call thermal noise. So in my everyday work, I'm basically trying to make better coatings and also use cryogenics to reduce this effect and make better mirrors for future detectors that let us see even further into the universe.
Welcome all to National Science Week Immersive Science 4, where we will take you on a virtual tour of the universe using the Science in VR app. My name is Professor Alan Duffy. I'm an astronomer at Swinburne University, and joining me on this virtual tour of the cosmos and the changing universe is my colleague, Dr. Rebecca Allen. We're so delighted to be able to join you all this evening. Thank you so much for taking the time on your Friday night to get involved with science. It really is just such a thrill to be able to share this evening's tour with you all. You've just seen a few of our fantastic researchers who are manning the Twitter feed, Facebook, and YouTube. If you have a question throughout tonight, use the hashtag AskSciVR, and they will get to those questions, or we will be able to answer them in real time live at the moment. So before I go any further into this evening, though, I want to pay my respects to the elders, past, present, and emerging, of the traditional owners of the land upon which I am streaming from, the Wurundjeri people of the Kulin Nation. I want to pay my respects to all Aboriginal and Torres Strait Islander peoples throughout this land. No matter where you may be watching this stream, we want to pay those respects to the first astronomers. And as we'll see tonight, some of the events have been recorded and faithfully orally passed on for thousands of years through the first astronomers' work. To better get a sense, I think, of that complexity and sophistication of the first astronomers, we actually have an acknowledgement of country seen. So what better way to get grips with the app? So hopefully you all have your headset, and if you don't have the headset or the little flips, hopefully you can just use this in the non-VR mode. But why don't we start off with VR mode, and we'll go click that button, and we'll take ourselves into the app. And then I want you just to look around, and if you have to move your head completely around to get the full 3D experience. We have got a lot of cool things going on. You can see the Hubble Space Telescope above your head. It's not that close in reality, obviously. We have, as I said, there's the laser beam shooting from the Keck telescope, which Swinburne has access to, and a number of us joining you this evening have used it for scientific purposes. If you pan down and to the right, you're going to see the acknowledgement of country seen. And there we go, beginning to swing round to the right. And at this point, I'm going to hand over to Rebecca.
So we are so excited, you guys, to explore this first scene. And I just want to say welcome to Kingston Library, Port Adelaide Libraries, and the Gravity Discovery Center in Western Australia. We're so excited that we're getting all of our regional events and our individual viewers to join us tonight. So let's look now at our acknowledgement of country seen. We're looking at a map which is spectacular because it highlights all the amazing peoples, Indigenous peoples of Australia. And so just like we're speaking English right now, all of these peoples have their own language. And so we encourage you to explore this map. And if you tap the green circle over a segment of the map, you're going to get a zoomed in view of that area. So I'm going to tap the area around Melbourne, and I can see that there's not just one or two little shaded regions, but that there's many. And I can actually kind of read what those are. And so take a moment to take in this wonderful map, and we encourage you to continue to explore it in your own time. But now we want to go in and explore this dynamic universe that our ancestors were the first ones to look at. So now we're going to go back to our menu, and we're going to hover over the home screen button. And when our green circle lights up, again, that means we're ready to interact. So let's go ahead and tap that green circle and go back to the home screen. All right. Now I think we're ready to explore. Alan, should we delve into the solar system first?
Yes, absolutely. All right. So if everyone goes, so for me and hopefully for you all, it's to your left. So if you pan over to your left, you'll see the solar system. There's a beautiful picture of Saturn. Get the green icon highlighting over and tap the screen to select it, and you should be transported beside a very large star. This, of course, is our sun. And then as you look off towards the right, you should be able to get a sense of all of the planets stretch out across the solar system. Now, there are a couple of different ways you can jump around this scene. You can either try to directly click on them. That gets a bit trickier because some of the planets are quite small and quite distant. Another way to do it is to look down at the menu where we have the planets arrayed, and you can jump between them. Again, always just bringing down the green icon and tapping on the screen. In our case, let's start off with Earth, right? Somewhere familiar. Tonight is all about exploring the changing universe. And for us on Earth, I think the most obvious sense of that is the fact that we have a day and night. So if you tap on Earth, you should be able to see. So let me just jump up. You should be able to see that the Earth is turning. Of course, we have the side that is experiencing day on the left, and the night side is on the right. The rotation of the Earth is about 1 hour of real Earth time is 1 second in the app. So we're getting a real sense of how that's moving. And we have the same planetary rotations is kept throughout. So if we look to the right, we'll see something like Jupiter, this massive planet, but it is absolutely whizzing around. So there it is, keep going. We can see it's making its full day in just about 10 hours. So incredibly quick changes. What else can we see from our perspective of Earth? Well, we get a sense, of course, of the moon, and we can change the phases of the moon, change its shape as we see different amounts of the sunlit side of the moon from our perspective on Earth as it goes around us. We see the motion of the planets over the course of weeks and months of the year. And if you're really eagle-eyed, you can actually get a sense of the change of their brightness as their relative distance to us and the sun changes, and they reflect more or less light. So those are all things that we can be familiar with, and certainly the people around the world have been studying and been aware of these changes for many thousands of years. What else can we learn? Well, of course, we can use telescopes, but the more fun way, I think, to explore a lot of this is to just go there. So if we jump to Mars, and there's the red planet in front of us. On this world right now, my favorite fact about it is that it is entirely inhabited by robots. I just love that idea. And right now, in fact, there are 3 missions heading off to the red planet. We have Tianwen launched by China, the Perseverance rover launched by NASA, and the Hope mission launched by the United Arab Emirates, the first Arab interplanetary mission. So even amidst a pandemic, people are still engaging in science. They're still aiming towards a future in which we discover ever more. And that just gives me such joy, I have to say, just to think about. So you can explore the rest of this scene and get a sense of how it's changing over time. And these are timescales that we're familiar with, right? You know, days or hours. What we've realized is that the universe is changing on timescales that are much longer, but also much shorter as well. And it's only relatively recent, like in the last few decades, that we've had the technology to allow us to look at those different timescales and unveil just a completely astoundingly complex universe. So if we're all done with solar system, Rebecca, have we had any questions yet? Any new additions, shout outs?
So while we're waiting to see if we have any questions, we have quite a few people who have joined our stream. Awesome. So we have the Ballarat Observatory, Prime Sci. Welcome, everyone.
Oh, hey, Prime Sci.
Discovery Center Bendigo and Twisted Science. Welcome, guys.
Fantastic. All right. Well, look, we now have a bit of an exploration of, so there's actually a hidden Easter egg in this. See if you can find a planet that's no longer a planet. I'll just leave it at that. Now, let's jump, I think, to All Sky. Let's explore another very familiar site. Rebecca, take it away.
Absolutely. So again, we're talking about these time scales and what we've learned. So let's go back to our home screen. So again, hover over your home icon, engage with that. And now you should be back to your main menu. Now all sky is going to be on the left there from the center. Wonderful. And now let's click that.
Mm-hmm.
Sky view, that's it. So all sky is quite a complex scene. And so what we've tried to do is build in a lot of different elements. So we're not going to cover, even a tenth of what's in here for you to explore. We're just going to highlight a few things, to really explore these extremes now of the timescales of events in our universe. So let's look at our menu, which is going to be really good for helping us guide us through. Now you're going to notice there's actually a cog at the top right of the menu. Let's click on that, and that's going to open some extra features. Mm-hmm. Now, we want to turn on some other layers. So let's turn on constellations. Let's turn on points of interest. And let's turn on the ecliptic. So the ecliptic is the line that we see the sun and the planets trace through the sky. And that's the same plane that we were just exploring in the solar system app. So now we're looking at it in the night sky. And constellations, well, these are shapes that help us navigate and map through the cosmos. So we're going to follow the ecliptic, and we're going to follow that line down, and we're going to follow it through. So the ecliptic goes through what we call the signs of the zodiac. So we can go through these different constellations. Now let's follow that until we get to the constellation Taurus, which is the bull. And near Taurus, we're going to find a very famous constellation known as Orion the Hunter. So I'll give you guys a second to find Orion.
In fact, while everyone's looking, Jing Wen has asked, what is the black line in the middle of the galaxy? And that is a lane of dust that sits along and blocks the starlight. And in fact, that's the plane of the galaxy itself. And that is very noticeable. If you go to the regional areas of Australia, for example, you will see so beautifully crystal clear that dark band in the middle, which Aboriginal astronomers, certainly the Gurungai people in New South Wales had termed the emu in the sky, and other peoples saw other animals and other stories that were associated with that very visible structure that you get to experience here in Australia. Awesome. Just jumping in while everyone was finding.
No, that's perfect. I love that we're highlighting, our history with the sky. So now if we go up from Taurus, we see Orion, and we're going to look down into Orion's belt, and you'll see M42. This is a special object, and I want you to click on M42, and now an image is going to pop up. This is the Orion Nebula. It is the birthplace of stars. And actually, you can see some bright blue dots and white dots, and those are young stars which have just been born. Now, we're talking about timescales here. A star takes about 1 million years to be born. And so even though, we think of our relatively short lifetimes, stars actually can live a very, very long time. So I want you to just appreciate. So what you're looking at here, that's a lot of gas and dust, which is collapsed into form these hot young stars. Now, if you click on the image again, it will disappear. And now we're going to follow Orion's arm up and find another object, M1. So I want you to click on this object now. So the life of a star is not always so slow. It takes millions of years to evolve. Some of them, like our star, will last for billions of years. But the most massive ones, once they get to the very end of their life, they explode, ejecting their materia at tens of thousands of kilometers a second. And that final explosion takes about a second. So very quick, very energetic. And what you're looking at here is what we call a supernova remnant. So you're seeing those layers that were blown out and are still moving through space very, very quickly. Now, this is the famous Crab Nebula, and at its center is the remnant of a dead star called the Crab Pulsar. So pulsars are fantastic objects because they have such strong magnetic fields that they actually send out radio jets. And those radio beams can be detected by our telescopes on Earth. Now, the Crab Pulsar is really whizzing around, and we get tens of pulses from it every second. So it is spinning very fast in the remnants of its, star surroundings that were there for millions of years. So something which is happening very, very fast, that was on a very long time scale. So things can change very quickly. And that's what's so amazing that we want to, really highlight tonight, is that some of the science isn't happening over thousands of years or millions of years. It's happening in less than a second. And so that's pretty amazing. Now, I want you to click on that image one more time. And you might have noticed, you might have been like me and a little bit excited after that image disappears, that where did my menu go? So one thing that you can do in this app is just hover your circle over a blank space and hold down for about 3 seconds, and your menu should just pop right up again for you. Now, we're looking at the sky in visible light, but visible light is just one way to explore our universe, and we have all of these other amazing detectors. So now I want you to, looking at your electromagnetic spectrum, and you see all the different wavelengths of light, let's click on X-rays. And you can tap the 3 bars on your menu to make it go away. And whoa, you will notice that now the sky looks quite different. And where we had M1, there's a bright blue glow. And that's because these supernova remnants remain hot long after the star has died. But interesting, the Crab Nebula is kind of young in terms of supernova remnants, in that it hasn't even been there for more than 1,000 years. And astronomers on Earth actually saw the supernova explosion in the year 1054. So that's pretty cool that we're looking at a relatively young stellar object. So it can be a little bit tricky to kind of see all of the different objects in X-ray. So I might just turn back to visible light, but please look around because there's some amazing other objects that you might find. So I'm going to click on my menu, and we're going to go click on optical light once again. And then the last kind of object that I want to show you before I turn it back over to Alan is we're going to go back over to Orion and follow down, and where we saw his belt, we're going to keep going over to another nearby constellation called Canis Major. So this is Orion's hunting dog, but very close to it is another object, NGC 2207. So we have just been talking about where stars are born and what stars look like when they die. But how do we get the right conditions for these stars to form in the first place? Well, what you're looking at now are 2 galaxies like our Milky Way that are in the process of merging. Now, this is something, again, shooting back out to those big time scales. It can take galaxies billions of years to get close enough where they're going to collide, like our galaxy and the Andromeda galaxy, and then millions of years for them to actually coalesce and come together, if that's what they're going to do. We won't get into that now. I encourage you to ask some of our other scientists online more about that. But what can happen is when these galaxies are colliding, they compress all of that gas that's in there, and then you can have bursts of star formation. So you can, instead of forming 1 or 2 stars a year, you can form hundreds, maybe hundreds of thousands of stars a year. And some of them are those very massive stars, that like the one that formed the Crab Pulsar, or they might be so big that they don't even go supernova, they go straight to a black hole. Now, this is the first time we're mentioning black holes. We can't see black holes. Nothing can escape them, not even light. But it turns out We have other detectors, like we're seeing the X-ray sky in our optical sky. We now have detectors that can help us see what happens when two black holes collide. So now, if you're still looking at your galaxy image, you can click it and it will disappear. And I'm going to throw it over to Alan, who's going to help you explore some other cool features of the scene.
Absolutely. Thank you very much. And welcome, Port Macquarie Observatory. Great to have you on board. So continue to ask your questions using the hashtag #AskSciVR. And I've seen that actually some of your questions have been answered by the actual world experts about those exact topics. So I'm not even going to pretend to try to answer some of those questions. You've literally just had the answer from, someone like Duncan who spent 20 years of his life working on this stuff. So thank you, Duncan, and all our other volunteers for answering these questions live. As Rebecca mentioned, we're going to now explore something a little different. We've mentioned the fact that some of the events we're seeing changing over the course of days in the case of a supernova explosion, or fractions of a second if it's a pulse from a pulsar. There's another event that occurs incredibly quickly and is something that gets us pretty excited, I have to say, and that, of course, is the collision of black holes. And I don't know what's going to show up now, because this is where the app will update automatically about what has recently been discovered. So if you can go down to your menu and select GW Events, Gravitational Wave Events, so hit the three bars, pull up the list, and you go down and select Gravitational Wave Events. These are detections that have been heard by LIGO. We'll get into that, a Gravitational Wave Observatory, and have just been automatically pulled. So the very latest events have actually now just popped up on your screen, I hope, and certainly have on mine. So if we select, say, second from top, if you just click on it, you should see below somewhere on All Sky where that event, which again has just occurred, or at least, just been detected, occurred many, many millions of years ago. And the gravitational wave signal has taken all this time to reach us. And there it is, that hotspot, that little red glow. That's where we have been able to tell that the signal has come from. These gravitational waves, these ripples in space-time have come from that direction. Now, of course, the key is, can you zoom in on that bit of the sky with optical telescopes, for example, like the Hubble or the Keck telescope we mentioned before, and see if there's a corresponding counterpart. So in other words, a galaxy that lies somewhere back into the universe along that location. And then when you can do that, you can start to do some very exciting physics with them. But for now, you can click through all these other events and try to get a sense of the different kinds of collisions. We have the reds are binary black holes, so that's two black holes colliding. Purples are binary neutron stars, so that's the dead remnants of a massive star, the neutron star, the core that's crushed into this thing that can also be a pulsar, if conditions are right. So a binary neutron star means two of those collided. The neutron star black hole, which is very exciting. So we have lots of different candidates. So obviously, in your own time, please explore, have fun with those. We will explore a little bit later about exactly how those gravitational wave events are detected or heard, as we like to say, using facilities like LIGO. But for now, it's something I just love to again get a sense of this, the timescales. These, say, two black holes will have taken millions of years to slowly get closer to one another, and then the last fractions of a second will orbit each other perhaps hundreds of times per second, almost at the speed of light, tearing themselves apart and then finally colliding. And that is this gravitational wave event that we get to detect. So something that was millions of years in the making, all over quite literally in the blink of an eye. And this is what we can now explore in this new era of the changing universe, or in what we call the time domain. Now, okay, there very likely could have been a gravitational wave event somewhere in the universe in the time we've been talking. I hope to be surprised by that. I was kind of hoping that might actually pop up and we'd see something. It's entirely possible. And the most science comes from when we get the gravitational wave event with LIGO, for example, and then also a counterpart using radio, optical, X-ray, you name it. All the other telescopes on Earth will swivel around to try to take a look and also see if, for example, if it's two neutron stars colliding, it will make a visible signature. If it's two black holes colliding, it's unlikely to. For this reason Rebecca mentioned, you can't escape a black hole, so it's very hard for any kind of explosion to escape them. Not entirely true. You could have something hanging around in the meantime, but generally speaking, this is one of the hottest topics in astronomy right now, is trying to find all these different combinations of the sizes of black holes, different combinations of neutron stars and black holes, everything else colliding with each other. And it's only when we bring in all of our astrophysical knowledge together that we can make the best use of it. All right, now, we've mentioned a lot. Yeah. So have we got questions?
I don't have any. I don't believe that there aren't any questions.
All right. Well, look, again, use the hashtag AskSciVR. I'm seeing answers popping up on my screen, so I know the volunteers are taking a lot of the questions, so that's awesome. We're explaining it too well, Rebecca, Collins says. Bless your heart. Okay, well, we've mentioned a lot about how, at the end of a life, you get a neutron star and all these other amazing kinds of objects. How about we actually explore how they form? So let's jump out of all sky. So we'll hit the home. Oh, and obviously it goes out saying there is so much detail in here. You could even change the orientation, which we didn't even do, but that's cool. Let's go to the home screen again. And now we're going to jump into Star Lab. So hit the house icon. And now get into the Star Lab. Don't hit exit. Yeah, where are we? There we go. So this is a little fun scene in which you can, well, see how the more extreme objects of our universe form. So hopefully you will, there we go. You're in the Star Lab now. Down below, you have 3 objects that you can try to form and see indeed how they form. On the left, we have a white dwarf, which is what the sun, our sun, will leave behind. The neutron star, Rebecca mentioned this really super densely crushed material. And then even more extreme is the black hole. We've got time, Rebecca, do you reckon, to do neutron star and then black hole? Should we
why not? Why not?
All right. So let's everyone start with the neutron star. So click the neutron star. And then just above your screen, you should have noticed some, colored circles have appeared. And then you keep looking up, and now a big star is sitting right there. So this is a very massive star, hot blue-white star burning its fuel incredibly quickly, as Rebecca mentioned. These things can be tens of times the mass of our own sun. But rather than burning that enormous amount of fuel in, the 10 billion years that our sun takes, they do it in maybe 100 million, right? So these are real rock stars. As they get towards the end of their life, which you can advance, because we don't have 100 million years to wait, if you click on them, you will see that they have, it now swells dramatically, as we all do as we get older. We put on the weight. In this case, it's just becoming bloated. It's actually, if anything, losing weight as its stellar winds share or throw that material out into stellar space. But this is now a red supergiant, incredibly swollen. These can be incredibly bright objects as well, but a sickly, deathly red. They don't last for long. One more tap, and we see the explosion that is the supernova that leaves behind this neutron star. So imagine something about the mass of our sun crushed into something the size of a city, an incredibly extreme object. As Rebecca mentioned, its magnetic fields can focus beams of radio emission or light along its magnetic poles. And in this case, it spins around and it has a lighthouse effect. And if you were to see that sweeping beam of radio emission to hit your eyes or your radio telescope, you'd see as a pulse. As we mentioned, some of these objects can be spinning as fast as a kitchen blender. It's an extraordinary object to think of something the mass of our sun spinning around that quickly. They really are incredibly extreme objects. And shout out to Jocelyn Bell Burnell, my homegirl from Belfast, who was the discoverer of the Pulsar. And we can now go for a slightly more extreme object. As Rebecca mentioned, let's go down to the black hole. So if you click the third option on the right, which is very, very tiny, because, you know, they are. So there's the black hole. And now when you pan back up, you should hopefully see you've reset the star. So we've got, again, it's another massive object. It's a little bigger than before, but not, you know, too noticeably so in this case. Hit the button again, or hit the star. It swells up, you know, some kind of a hypergiant, and then we hit it again, and we get the object collapses into a black hole. How do we see black holes? Well, we've said many times that light can escape and the gravity is too intense. That's the black bit of the black hole. You could see material swirling around and falling in, heating up incredibly to incredibly high temperatures. And indeed, the brightest objects in the universe are the black holes, or rather the material swirling around them. We can explore the gravity of this black hole in the Star Lab by going down to the cannon. We have ourselves a neutrino cannon. So if you pan down into the right, and who could resist hitting a big red button? So hit the big red button, and it should fire out a cannon ball of neutrinos. These are ghost-like particles that fly through even the Earth, essentially, without any challenge. In our case, they're flying through our little Star Lab. And importantly, they're flying around the black hole, pulled by its gravity into orbit. And they're actually being stretched out. And eventually, they would form, in reality, a nice kind of an accretion disk, as material would slowly but surely feed into the black hole. You can play with the different settings of the cannon. Our default, because I kept getting it wrong and I couldn't manage to do it, was that we could fire it into orbit, but you can change the direction and the speed to play with different orbital configurations. That is, of course, something for you to do after this. I think we're pretty close to finish with Starlab. I think maybe just one more thing. What we see as the motion of those neutrinos going around the black hole, they're actually traveling in a straight line. It doesn't look it. It looks like they're curving around. They're traveling in a straight line, but through curved space-time. So the black hole's mass is curving space-time. We can't see that four-dimensional space-time with our eyes. Instead, all we see are objects that should be moving straight through four-dimensional space-time are taking this curved path around the object in the normal 3D that you and I experience. And that curvature is key for how we detect them with the gravitational waves. So, very exciting stuff. But before we jump to those, have we got questions?
Yeah. So we've got one question, and I think this is fantastic because we've touched on it just a little bit. So Rudra wants to know, what are the factors that cause pulsars to spin so fast? And I think that's a terrific question, because the fact that it is spinning so fast is actually why it's a pulsar. So Alan, do you want to explain a little bit more about that?
Yeah, absolutely. So great question, Rudra. We have, as the objects, as any object, even let's think of, say, the figure skater, ice skater, as they spin around and they bring their arms in, they spin faster, right? And that's because the term is conserve angular momentum. In other words, the same amount of spin, if your arms are spread out, or say you're a star that's nice and spread out, like the red supergiant was, very, very large. As you then bring your arms in, or in this case, material is falling onto the neutron star, or so that core, it's having to spin faster and faster. Again, that's the ice skater bringing their arms in. And by the time you've got all of that material and you've dragged it to something that's just the size of a city, just tens of kilometers across, then it's spinning around incredibly quickly. So that's how standard pulsars, there's nothing standard about them, they're extraordinary, but that's how pulsars form. But there's an even more extraordinary class of pulsars, and they are called the millisecond pulsar. And these are the ones that really do go around like a kitchen blender in speed. And the way they speed up is because they're a normal pulsar and they're spinning, but they have a companion, another star beside them. And as it evolves and it swells up towards the end of its life, its material now gets too close, gravitationally speaking, is pulled over the Roche lobe, if you want to get technical, but anyways, is pulled onto that pulsar, and it begins to steal the material. And because it's pulling this material down onto itself, it's taking that angular momentum and it's speeding up and it's spinning up. And over time, and not too much time actually, these things spin up to the incredible speeds that we see, hundreds of times, rotating hundreds of times a second on their axis. So these are the millisecond pulsars. And if you've ever listened to an audio play of millisecond pulsar, it is the most annoying drone you've ever heard. It makes mosquitoes sound pleasant. So these are very strange extreme objects. They are also super accurate clocks, and you can use them to test Einstein's theories, but we'll probably skip that for now. Unless someone has a follow-up question. I'm not inviting that follow-up question, by the way.
But I think that's one thing that's so fascinating about astronomy. So like you were saying, Jocelyn Bell, who detected the first pulsar, is that pulse of radio energy. And the frequency that we get those pulses is what we define as the pulsars, period. And it's that timing which is telling us about the physics that we're actually detecting. And so I think that's one thing that's so incredible about pulsars, is that through those little packets, those little bursts of radio energy, we're able to unlock all of this physics. And so speaking of these incredible objects, so we've gotten to see plenty of stars explode in this scene. And so we're actually now in the next scene. We're going to take you guys on the hunt with some astronomers who are working at Swinburne to catch these supernova explosions happening in real time. So let's navigate back to the home menu. So in this scene, you can either tap to bring up your menu, or there's actually another big red button. There we go. You can press home there. But if you get a little bit discombobulated, down on the bottom left of that panel, there's also a home button. So now Carl's taken us back. Carl, thanks. Shout out to you for being such a great navigator. So now we're back in our home screen. And so let's go down to our icons and spin all the way over to the right to where we see Baker Room. So now we're going to enter the Baker Room. This is a facility on our campus where we are actually able to connect with telescopes across the world, like the Keck telescope in Hawaii. And that's pretty spectacular to think that you're in Australia and can actually control a telescope in Hawaii. Now, what is great, we're looking around here, is this facility is very high tech. We can take observations. And what I want you to do, this is a 360 experience. So make sure you're looking all the way around and exploring this room. But what's going on here? So we have a group of astronomers. I actually happen to be part of this awesome team. And this is what we call the Deeper, Wider, Faster survey. So it's using all of the wonderful types of telescopes and detectors we have. So our radio telescopes, like we were just talking about, optical telescopes such as Keck. And what we're looking for is perhaps Parkes has detected what's called a fast radio burst. So like a pulsar, but an order of magnitude more energetic. And then we can actually say, you know what, telescope in space, we want you to slew over and look where we think that radio burst just occurred, to look for what's called the optical counterpart. And that's what Alan kind of hinted at earlier, is that being able to use these different wavelengths of light, we can actually understand more about the physics of what's happened. So if we catch that explosion, the details of that explosion tell us, are we seeing two neutron stars that have just collided? Or is it a regular old supernova? Or perhaps it's one of these dwarf stars that gets temperamental and has a flare of radiation. And so the Deeper, Wider, Faster survey has been going for a few years now. And in each survey, they detect dozens of these flare stars or variable stars, and maybe a handful of supernova. But they are yet to catch the big, what we call kilonova event. So stay tuned. Again, things that are happening in real time. So cool. So, Alan, did I miss anything there, or did you have?
No, just Jeff Cookie's work has been fantastic. So thank you, Jeff, for your leadership, and for the Graham Goldsmith Family Foundation for actually supporting the Graham Baker Foundation. Sorry, for supporting. That was our old chancellor, for supporting this facility. It really is unique. Welcome, by the way, Mount Burnett Observatory in our home state, Victoria. Where have you been? Lovely for you all to join us, though. I assume you were just shy. Assume you're on time. All right, we are now going to jump into LIGO. We have been speaking repeatedly about gravitational waves and this mysterious LIGO. So why don't we hit the home button? There's the house. In my case, I'm actually going to have to move my map. My menu out of the way now that I've gone back. So if you get lost with your app, just hold your finger on the screen and it should reappear close to you. So hitting the home. And then if you go to the LIGO scene, now this is between Starlab and the Baker Room, that squiggly line. So if you hit that, alrighty, now you should be sitting inside a R version, or rather Carlo Mark from Osgrav's version of the LIGO detector. So this is the Laser Interferometer Gravitational Wave Observatory. LIGO is basically a super accurate ruler, or rather a pair of super accurate rulers that are designed to measure the stretching and straining of space, of the Earth, of us, as these gravitational waves pass through us, caused by the collision of epic things like two neutron stars or two black holes colliding. So to get a sense of just how extraordinary this facility is, we're going to switch on the laser beams, because of course it's laser beams. What good science doesn't have frickin' lasers? Hit the green button and we will see a laser beam fire out. It hits that first bit of material that's called a beam splitter, and that separates one laser into two, and they go zooming off down these 4-kilometer long arms. In reality, these would be entirely in vacuum, and bounce off mirrors. And we heard before about some of our ANU colleagues who are doing extraordinary work to improve the material of those mirrors. It bounces repeatedly back and forth down these 4-kilometer arms. But the key is at the end, the laser light comes back together. It has been moved just exactly out of phase. In other words, the peak of one laser wave would cancel in the trough of another, essentially meaning by the time they get recombined back at that screen, you have just essentially, a static, or if it was perfect, you would have basically black on that screen. As it is, it's like the old timey-wimey TV screens fuzzing away. So we have these 4-kilometer long rulers, and we are looking for them to move when stretched, as the space-time itself does, as the ripple from a gravitational wave event passes through us. To get a sense of the LIGO can detect the change of 1/10,000th the diameter of the proton in the center of the nucleus, in the center of an atom, and an atom is impossible to imagine how small that is. So another way to think of it, which is not that much more helpful, quite frankly, in terms of accuracy, is it can measure the distance from here to the nearest star change by the width of that human hair. From here to the nearest star, 4.2 light years away. This is an extraordinary instrument. Now let's create a black hole merger. So if we look down, we get our two black holes. If you press, you will then find two objects beginning to fall together. Well, firstly, you've just seen this, the screen is already changing, right? So now it's beginning to flicker rhythmically. So if we look up, we can see what's causing that. And we see that there are two black holes spiraling around one another. This is a dance that can take millions of years as they get ever closer. But the final seconds, essentially, or fractions of a second indeed, that LIGO can pick up is what we're focused on at this point. As they spiral around, they kick out waves, these gravitational waves. They pass through the detector. They change the length of the arms, so the laser beams don't perfectly cancel out one another, and we're left with that signal, and that signal is going back and forth, exactly like the black holes are spiraling in together. This is essentially a sound. This is what a sound is. It's the wave going up and down, and it happens at about human or audible hearing. So we can do another, wonderful, thank you. So there's a, so where are we at now? If we can just pan up and see what's the status of the object. Okay, they've got a little while left to coalesce. By the time they're beginning to finally merge, they're making hundreds of orbits of each other a second. Impossible to imagine when they're tens of times the mass of our sun each alone, faster and faster and faster, almost at the speed of light. And then they merge into a single object, a new, bigger black hole, which isn't exactly the same mass as the two previous ones. In fact, it actually converts the mass of some of the two black holes into pure energy, into these gravitational waves. In one notable case, the first one we've detected a couple of years ago, this was 3 solar masses, so 3 times the mass of our sun was converted directly into energy, into these gravitational waves that all released in this last fraction of a second. It is the most powerful explosion we have ever directly seen. And the whole thing shook and changed the LIGO detectors by, again, a fraction of the size of the proton in the center of the atom. It's an impossibly weak signal. It took a century of searching to find, for very good reason. Exquisite engineering has made this possible. And it really is still, to my mind, one of the marvels of modern astrophysics, that we can hear these gravitational wave events, turn the telescopes, then look for the afterglow of the explosion. And in particular, if you get 2 neutron stars colliding together, they will release a lot of light, and they will also form an entire planet's worth of gold, which I just think is one of the more fantastic ideas. So in that fraction of a second, objects that may have been lying there for billions of years convert themselves into, at least some of it, into pure gold, like the gold that I have on my wedding ring right now. So this was forged in the heart of 2 colliding neutron stars, millions to billions of years before our solar system itself even began. So everything we do in astronomy is the timescales are incredible, from billions of years to form to fractions of a second to fuse in new elements. So very cool stuff. And we really have only discovered these things in the last handful of years. So again, it's very much a very dynamic universe in reality, but also scientifically, because we're discovering new things all the time.
Now, speaking of the incredible engineering that it took to build the LIGO detector and the other detectors that we now have online, I want to give a shout out to the OSGrav Adelaide team, who have built their own LIGO detector in Minecraft. And so 2 p.m. tomorrow, Adelaide time, on YouTube, check out their YouTube channel, because you'll actually be able to get a little tour of it there. So whether you like to explore it virtually, whether you're like one of the super exclusive people that gets to see it in person, or perhaps you want to check it out in Minecraft, there are so many ways to explore these different detectors. So I think that pretty much brings us to the end of the scene. Go ahead, Alan.
Yeah, well, I was about to say, we have a question, and this is definitely one for you, Rebecca. Linda has asked, what observatories beside Keck can you connect to from the Baker Room?
I think that's a fantastic question, because we have to be very secure in the way we're connecting to the telescopes. So that means we can't just call up any telescope. And we can talk to pretty much the operators of any telescope, and that includes the space telescopes via the Baker Room. But to actually control them, there's only a handful of telescopes that we can do that with right now. And so as we continue to work on that, then the hope is that we can do that more easily. But as Alan and I can both tell you, there's still nothing that compares to actually traveling to a telescope. Like we both got to go to the Blanco telescope in Chile. And I get to do it for the Deeper, Wider, Faster survey. So, it's great that technology is enabling us to do that. But it's still nice when we can travel again to get to go to those fantastic observatories.
Yeah, I think the record for the Baker Room was I think it was 35 separate telescopes, including orbital, like Hubble. I mean, pulling in data from across the globe, really almost every wavelength imaginable. Really cool stuff. Right. Now, we have essentially explored the universe. So maybe we'll just go back to home. So we'll hit the house icon. And you can get a sense of a couple of those telescopes we've been mentioning dotted around. I just want to give a couple of quick shout outs to amazing Australian facilities like ASCAP. There it is on the bottom left, the beautiful dishes out in WA. I'm pretty sure we had Meerkat off to the right there. On the mountaintop, we've mentioned Keck on Mauna Kea in Hawaii. Of course, there's the orbiting facilities like Hubble. Other incredible Australian facilities have made these discoveries possible, like the AAT, looking for these explosions and finding exactly where they came from in follow-up surveys. Parkes, which is now heritage listed, which is wonderful. So congratulations to Parkes for that. And Utmost, which is this mile-long cross-shaped radio telescope, which is wonderful and super, super strange. They are all exploring the universe on different timescales, from minutes and days, where it's a supernovae, to the blink of an eye, indeed less than the blink of an eye, with fast radio bursts. We haven't really mentioned them much tonight, although they are there in all sky, the latest events. And part of that's because we don't really know what they are. we don't know what causes these fast radio bursts, but essentially something outputs nearly a century, about 70 years worth of the sun's entire energy output. And all of that occurs in less than the blink of an eye. So we're talking milliseconds, and these explosions occur very bright in the radio, not been seen in anything else. There's about 10,000 of them occurring throughout the sky each and every day. It is a very big mystery. We don't know what they are. We only just discovered these things were occurring in the last few years. So, and again, it's Australian facilities like Parkes and like Utmost, for example, that are really forging ahead. So I hope that you're all feeling a little prouder or a little more informed, and also prouder of these incredible facilities and the work that's been done and the mysteries that we are uncovering, quite frankly, as well as solving in our changing universe. We have a couple of minutes for any last minute questions. I don't know, did you want to share anything else, Rebecca, that we haven't mentioned? Oh, okay. We have a question. What's cooler, black holes or neutron stars? Rebecca?
I mean, are we talking, literally or figuratively? So I think that's a fantastic question. I would say black holes are definitely hotter. And we even get black holes, and that's because, we've been kind of talking about the stellar mass regime of black holes, but there are black holes, that lurk at the center of galaxies like ours, which we call supermassive black holes. And so these things are just gargantuan, and they are able to warp space around them and superheat any gas that even thinks about coming close. And so I would have to say that neutron stars are cooler, but black holes are cooler, if you know what I mean.
Okay. There's a great question about, and I didn't do a good enough job explaining the LIGO signal, what a given LIGO signal represents. So we have that little squiggly line as the icon. So maybe we'll just sort of pan down and just remind ourselves about that. That's the waveform. That's the signal coming in of the ripples. So it's thank you. Yes, so you can remove your menu to see it better. So it starts off as a slow, and then as the black holes spiral in together ever closer, it's happening at a quicker pitch, or quicker orbit, so higher pitch. So, and you can see it's increasing in amplitude, so it's getting louder. And then the chirp ends, and it ends because the two black holes have become one and stop rippling, essentially. That last little bit of a ring down is where so much of the exciting science is right now, where you're getting a hope of probing the event horizon of the black hole. So lots of fantastic science occurring. These signals are just so well predicted by Einstein's GR that essentially we just match, we go through the data and look for those kind of signals on supercomputers. Siva has asked, how do you know what is in a black hole? Rebecca, do you want, to try to answer?
Is that we have no idea what is in a black hole. No. And it's, presumably this place where our current understanding of physics breaks down because it's such an extreme environment. And so, Siva, I will throw it back to you, because we are going to be relying on future astronomers and theoretical astrophysicists to delve into the mathematics of perhaps a quantum gravity or some kind of formulation that can help us understand what happens to matter and to space itself in these extreme dense environments. So we don't have the answer yet, but that's what's great about studying things like gravitational waves, is they're actually helping us confirm that, we kind of have it pretty much right so far in terms of our understanding of space-time. And then maybe the more we can explore these extreme objects, we will begin to kind of unlock that physics that is in the realm of the center of black holes.
Let's hope. Now, we have come to the end of this evening. Keep asking your questions using the hashtag AskSciVR. Again, on Facebook, Twitter, in the YouTube comments. There are astronomers who volunteered from across Australia to answer those questions after the show as well. So thank you all to them. You can catch us tomorrow at 11:30 Melbourne time. Have I got that right?
Yep.
For the family show. So we hope to see you all again then. Thank you all for joining us, from our regional viewers, our individuals. We're so pleased that you're able to join us this evening and brave a pandemic, no less, to learn more about a virtual universe. I think I just have to, at this point, acknowledge the incredible work of our OzGrav team. So Lisa, Jackie, Carl, Mark, you are all superheroes. Thank you so much for the work. Thank you also for deciding to do this for a fourth year, you crazy people. Also for the support of Swinburne University and the ARC Centre of Excellence for Gravitational Wave Discovery, OzGrav, and of course, the Inspiring Australia grant that makes possible National Science Week. Thank you all. And a special shout out for our Auslan Consulting and Auslan Services, who have been providing incredible accessibility and support throughout all of this. And I think also creating potentially new scientific terms in Auslan for some of the things we've spoken about tonight, which is kind of cool. Rebecca, finally, thank you for again joining me, and also no less for joining me from across the world at some horrific time for you in the United States of America. Thank you for making possible this Science in VR Part 4. It's always a pleasure to explore virtual universe with you.
Right back at you, Alan. It's just fantastic for us to get to share all of the incredible astronomy that's going on. And who knows? I think we got SciVR 5, guys. So
oh no, it's too soon. Too soon.
You can enjoy the app all year round, and we encourage you to go back and explore some of those scenes, ask more questions, and thank you so much for joining us tonight. Bye, guys.
Stay full.